Okay, right. My name's Ian Wells. As you can tell by this very old T-shirt, once upon a time I used to work on Openstack because I used to work a lot on NFE, and NFE involved a lot of Openstack in those days. I'm going to talk to you today about edge computing and how OPI can help us work here. I feel a bit embarrassed to follow Debo, actually, because while Debo is busy trying to build Skynet, I'm trying to make sure that it can reach your toaster to take it over. It's not so exciting, but it's very much the network-centric side of the world. Obviously, the first question in any edge presentation has to be, what is edge? So I thought I'd change that out a bit and say, why do we always ask what edge is at this point in the presentation? The answer to that is it means very different things depending on what we're doing. From a networking perspective today, the edge that we're going to be talking about is the smaller devices, typically sort of customer premise devices, sometimes edge of a service provider network devices, where what we're looking for is often quite a lot of functionality, but we know that we're putting it in places where there's a limited footprint, there is, constrained resources, poor cooling, this kind of thing. And the reason I bring that up is because the next question we ask is, you just heard that bit, the next question we ask is, what are the most important considerations at the edge? Now, with that definition of edge in hand, there are two things that matter, and these are fairly universal. One is money, one is power. The reason it's money is two things, really. One is I am about to deploy, say, 10,000, say 100,000 or 1 million devices on the edge. Whatever each one of those devices costs, it's going to cost me 1 million times over. So every dollar, every cent is of concern when I'm deciding what to deploy at those edges. And I'm trying to work out how to basically maximize my efficiency in order to get something out there that is of use, that serves its purpose. There's another cost element, which is, I like making money. So what I want to put out there, I want to be able to make, sing and dance. One of the hopes I have here is that I'll be able to make things sing and dance when OPI is involved. And on power, at these edges, we're not talking, the data centers that we normally work with, where power is in abundance. I've had plenty of places where power is not in abundance, but at least in theory, we have good, strong, clean power and plenty of it, and we have good cooling to go with it. If I'm dealing with these edge components, then I have limited quantities of power and limited environmental control as well. So actually dissipating that power can be difficult for me. So we work with effectively two technologies today, ASICs on the edge, right? We're Cisco. We build nice forwarding ASICs to put in our routers, in our switches. These are the things that we take to the edge as we take them into the core and everywhere else in the network. We decide precisely what they're going to do, and we design a chip that does precisely that. It is efficient because it's doing the task it does, no more and no less, in the most straightforward way that we can possibly manage. But it's not fast or cheap. It takes a long while to design an ASIC and longer still to test it to the point that we dare give it to anybody. And that process is expensive. And then when we're doing it, then it better be mass produced, or alternatively the cost per unit becomes ridiculously expensive. And we kind of hope that none of our engineers have any bright ideas, because we built the ASIC to do one thing. So if they come up with a different way of doing networking, some new protocol, some new technology for forwarding, then we have to spin up a new ASIC, from start to finish. We have to design another ASIC that does exactly that. So it actually limits our creativity. We can't do clever things because our ASICs will only do what we design them to do. We might be able to use them a little bit off books in terms of what we designed might have a slightly different use, but we can't make them do dramatically different things. With NFE, and here I'm talking about the idea of doing virtualized networking in software, we can do literally whatever we want. I can write software to take a packet and, turn it into 15 packets, all unique and different and special, write new encapsulations that no one's considered of, change the rate that packets are shipped. I can do whatever I please because software is effectively infinitely flexible. And we do it with custom code, not custom circuits, which I like because I write code. I'm not very good at designing circuits. And we can develop new ideas quite fast. We can prototype them. I can write them in terrible code just to see if they're going to work, and then I can make it production ready. But we can't do it efficiently. If I'm using a general purpose CPU to do networking, there comes a point where I need more CPU than anyone's willing to put in any of those edge locations. General purpose CPU is never as efficient as an ASIC. That's my problem. I'm compromising between flexibility and resources. So I'm looking for balance here. And to be fair, on that balance, no system in production anywhere in the world uses just one solution. Any router or switch that we produce will have a piece of software in it that controls a piece of hardware that does the forwarding. It is always that way. If processing a packet becomes too technologically difficult to do in that hardware, I'll punt it to software and I'll do it there. And that balance has varied over the years. In fact, any general purpose server, any laptop will have a NIC that will do some of the processing of packets before it hands it off to software, even if it's only fragmenting TCP streams, breaking those up into packets. There is some amount of offload that happens. The question is in finding the right balance that gets me to those magic things of nice low power consumption with high powered delivery of functionality, and again makes me the most money without while costing me the least to produce a device. And so that's where the hope of programmable infrastructure exists for me and for people in my position, that there is a new balance to be struck where hopefully we can find some balance where we are getting the CPU to be perfectly right sized, not the biggest, meatiest Xeon that I can lay my hands on, but a CPU of moderate power consumption, of moderate abilities, of moderate speed, to keep the money cut down, to keep the power consumption down, while at the same time taking infrastructure which is no longer absolutely set in stone from the outset, but flexible, where I can repurpose it to do what I'm looking for, which increases the money I can get for this. It increases my ability to change my mind about what I want to do, to try new ideas, and the power that comes from being able to deliver new networking technologies as flexibly as we possibly can. So again, flexibility here is the key. There are many smart NICs in the world. There are many previous technologies in the world that work with this. OpenFlow is an example. We decided, I think it's about 10 years ago now, that OpenFlow might be a technology that would work for us. And we still have OpenFlow programmable switches in the world. But OpenFlow is really just one idea for this. It was good for some things. You could literally do anything with it. But it misses out on many optimizations that we would normally do in routers. So route tables is a straight example. There are many things that we do to packets that are straightforward behaviors that we would expect our hardware to help with. And in OpenFlow, we were effectively programming in machine code when what we wanted to program in was a slightly higher level language. There are also many feature mix. Feature NIC is a term I would coin to talk about things like Intel or Mellanox's base generation of NICs, where there are things like flow steering. There are abilities within the NIC, but they're not incredibly advanced. They can help, but they have a fairly limited subset of abilities. And then smart NICs going a bit further, where there might be CPU, where there might be some programmability involved. Smart NICs go all the way up to Intel's M3000 series, which is actually basically a couple of network interfaces and an FPGA to do with what you will. The problem is we never really found the balance here between infrastructure that is easy to program, that I can experiment with, an infrastructure that becomes either too rigid, too set in its ways, or too complex, so difficult to use that in fact it becomes difficult to make it do anything of use to me. And a solution I can't easily use costs me to use because it takes more engineering time. It means more time to market. It means more engineers. And ultimately that costs me in money. I can't work with that. I need something that finds a better balance in the middle. So the promise of OPI to me is a solution with the flexibility that justifies its cost. I'm hoping that the hardware that we turn up with here hits a sweet spot, both in terms of the price of the hardware for me to put out when I buy 1 million units and try and put it into the edge. And it also offers me the flexibility that I'm looking for to actually program in both the ideas that I have and the ideas that I will have in the future. I'm hoping here for an API that considers what developers are trying to do. In this instance, I think open development here brings rapid feedback from end users that they can potentially obviously jump in and change the code. They can make it do what they need it to do, but also that they can give feedback to say, I see what you were trying to do here, but this actually doesn't work for me. And I would say as a community, it's important that to be a success, you have to listen when people say, this isn't working for me, this would work better for me. I'm looking for more flexibility in development. I know that I can go out and buy shiny new hardware, but the problem that comes with shiny new hardware is it tends to be great and it tends to be 6 months out, 1 year, 2 years. One of the advantages with the definition of an API is that I can simulate that API in software. Simulate is perhaps a bad word, but there is an implementation of that in software. If I can get things moving in software with a rough idea of how well it will perform when I transfer it to hardware, then I can start developing my ideas long before the actual hardware that I need is available on the market. And similarly, if I can move from one generation to the next without changing my code, I can make my code perform better. I can build it with additional functions in the future. I don't have to dispose of everything I've written. I can keep moving with the code that I already have. So these are the hopes that I have for OPI within the networking world. That's my last slide. I hope that's a relatively brief presentation, but I'm happy to take any questions or actually comments really from anyone who wants to raise anything.
Thanks. Reminder everyone, type in your questions. We do have one. What DPU, IPU APIs would you like to see to enable edge computing to be easier to use?
That's a very, very broad question. I don't know that there is a simple answer to that. I think when it comes to packet processing, the things that I see that are interesting are that we use encapsulation fairly regularly, but that encapsulations are not fixed and the forwarding of those encapsulated packets is not fixed. So something that gives me the flexibility to experiment with things that are not standards, but might one day be standards, I would be interested in that. I personally feel that, and this is going to sound very weird to anyone who works in networking, that we've missed a trick with multicast over the years. We made multicast with what turns out to be an intensely complicated control plane, very difficult to look after, which means that multicast gets used, but gets used in very specific purposes. So I wonder whether replication of packets is an area where we could do more, where we're not delivering on the promise at the moment, and where we should probably revisit what's possible.
Thanks. Okay, how important is an open ecosystem to the programmable edge?
Well, that's an interesting question. I would say one hope I have here is that, speaking to an Intel audience, that I'm looking for people to keep you on your toes, basically. I don't want to see this being the only thing I could possibly use now and forevermore is something from Intel. I want you to be developing with a degree of either competition or cross-pollination from other people's ideas. I don't feel that, and I would say this as Cisco as well, I think this applies to us equally. I don't think we do our best when we're the only game in town. So I'm looking for the creativity and the ideas of as broad a community as possible to be incorporated into what we're doing here, whether that is new and better and faster hardware, new abilities within that hardware, new abilities obviously within the APIs, because it's ultimately the APIs I consume and I care about. But, you know, I think both in hardware and in software, and I could take OVS as an example here, we get set into very rigid ideas of how the world works with networking. You know, networking is what OVS will do, is may be the way we end up going, but it's obviously not the truth. Networking is a much broader topic than that, and I want to be able to apply imaginative solutions to what I do. So I want people's imaginations to run wild and see what it creates.
Thank you. Is it possible to collapse all configurations so that an application packet queue in a container in a VM is directly fed by a NIC or a smart NIC? Could eBPF be used to achieve that goal?
Certainly that's true. You can do that, right? The historic way of doing that is SRIOV, which is largely a hardware technology. I think the way I would phrase that is that we get very set in our ways. There are three components here. There is the software, the actual kernel code in this instance that provides packets to a container. There is the hardware in the server, the NIC itself, that deals with providing packets to the kernel and can do some preliminary work on that. There is the hardware within the network, which can also be used to do some of the work before the packets get to the server, before they get to the container. We often find, I see, that we only deal with one of those, because dealing with more than one of those starts getting complicated. As an example, Calico within Kubernetes is pretty much entirely a software solution. It's rather difficult to enable it with hardware. Cilium, again, is heavily a software solution. It's difficult to bring advantages to it with hardware today, or at least that's not how people were thinking about it originally. I want to see, in the long run, networking solutions that use all the advantages of all three of those things, but at the same time are still maintainable and still operable, because I start to cross awkward boundaries within a company where that network fabric is maybe not controlled by the same ops team as the infrastructure on the servers. But in the long run, we want to be bringing the strengths of all three of those components together to bring a networking solution.
Thank you. Would having an x86 on a card be sufficient for the edge? Do we need an FPGA as well?
Well, it's a balance, I would say. If I'm sticking an x86 onto a PCI card and calling it a network card, then aren't I just sticking another server inside the box that already contains a server? And if that's what I'm doing, then why don't I find other ways to package two servers inside a box? It's got some advantages, and there are ways in which it does bring strengths, like, for instance, a general purpose CPU that is tightly coupled with and helping along with the processing of packets. But effectively, just finding other ways of stuffing more CPU into a box is not the answer here. I don't want general purpose CPU, because general purpose CPU is not the most efficient way of processing packets. It can certainly do it, and it can do it well, but it can't do it as well as dedicated hardware that is solely aimed at producing packets. Now, certainly I can bring opcodes to CPUs that have particular advantages to processing packets in much the same way as we've developed opcodes in CPUs that are particularly advantageous when I'm doing AI or when I'm doing gaming even. But I don't think the answer is to bring a standard CPU and say, this is my magic answer to all things networking.
Alrighty. Are there lessons you learned from your years in Openstack you could share as words of wisdom for those of us forming a new open source community?
So I think that's an interesting question, and it's a hard one to answer. And I know that Kyle's on the call here, and he was a project leader within Openstack, so I will call him out and refer you all back to him. But I think focus is important, bearing in mind that you've got to pick your targeted use cases and actually target them. Too many of them and you spread yourself too thinly. Openstack, in many regards, had about 100 projects at one point. So it meant that everybody, there was a lot of work and it was all interesting, but we weren't concentrating on single things. We were spreading ourselves very wide. The other thing is, from a networking perspective, there is a concept within cloud compute in particular, and this is true in Kubernetes and it's true in AWS. Openstack is not the only thing that owns this problem, that networking is one thing. In AWS, it looks like a layer 2 network. In Openstack, for their NFV purposes, it generally was a layer 2 network. In Kubernetes, it goes entirely the opposite direction and says that packets are not interesting, reachability is. There is not one flavor of networking in much the same way that there is not one flavor of storage. In storage, I like object stores like S3. I like file systems that I can mount. There are other cases for storage as well. Networking works in the same way. Remember that if you believe you understand the entirety of networking, somebody will come with another idea and surprise you. Don't be blindsided. Don't assume that your solution to networking is the only solution that can ever be true.
Okay, great. Are there any edge environments you've seen that have specific constraints that may prevent the use of a DPU? What are those constraints?
I don't think so. I mean, I worked on Rakuten's RAN edge, which is the radio edge of a mobile network, and it had a particularly constrained footprint. But even then, we managed to sneak in some acceleration cards. Power will get more and more constrained. I can say that safely. There are, many ideas that involve sticking CPUs into Wi-Fi access points, which practically speaking is already the case, or sticking CPUs into base stations at mobile edge environments where power is difficult to work with. But I don't think putting a DPU there necessarily is prevented. What I do think is you have to remember how often some of these sites are going to be accessed. A friend at Verizon once told me a story of a mobile radio site that was at the top of a mountain where somebody had to walk up the mountain with the equipment in their backpack. So, it needs not to be replaced very often. It needs to have a long lifespan. And apparently it also needs to be fairly light if you expect somebody to carry it up a hill. But bear in mind that, there are plenty of these circumstances where you don't want to change the equipment out with every new generation. It's got to have a lifespan that's longer than your current idea of what you're going to use it for.
Okay, another question. Describe how 5G is different than edge computing and how DPU IPUs may benefit 5G networks. So I imagine the benefits may be the same, but would love to hear your perspective.
5G isn't necessarily different from edge computing. You're talking at two different directions. 5G is a thing that you do with networks. It just so happens to benefit from edge computing because, and here it's not specifically 5G, the radio edge that I was talking about in Rakuten was actually a 4G solution. But 5G strongly suggests that the radio edge is going to be compute-based, and it is network intensive, obviously. So it rather suggests that that there is a compute edge, a very distributed compute edge at the edge of a 5G network. Effectively, edge compute with acceleration benefits 5G, but it's not just 5G that it benefits. There is a router in every home. Imagine if those things were enabled with programmable infrastructure. There is a router in every office. Imagine if those things were enabled with programmable infrastructure. Don't get too wrapped up with 5G as one use case, because it is only one use case. There are many use cases out there. I think that question was quite long. If that wasn't a sufficient answer, then please recap the bits that I missed.
Okay, next question. Explain any concerns you have around deployment and operations of IPU DPU devices in terms of edge and how OPI can help to solve those issues to enable its success.
Right. The usual comment here, particularly from networking, is how disruptive are things like upgrades? And it's interesting here because I find that network engineers forget this as well. Every maintenance operation comes with a disruption of some variety, of some length. The question is not how do you get rid of the disruption, the question is how do you minimize it. But if I am going to change the software on the server that is managing my DPI infrastructure, then what's going to happen, right? What is going to happen to my networking? How do I keep it flowing ideally? How do I make sure that firewalls don't magically open for a few seconds over the course of an upgrade? Think in those terms. It's not about seamless upgrade maintenance, because there is no such thing as seamless in most cases. It's about understanding the impact of such things. There's a whole much more about that in terms of distributing, new software, new firmware, and all the rest of it that I won't go into detail with. But I think from the lowest level, then impact is the question you need to be asking yourself about.
Okay, we've got another question. So the hardware needs to have a long lifespan, but the software would then also need a long lifespan. So does that mean that supported distros from stable companies would be important to guarantee updates and support?
Right, this is software philosophy, so forgive me for taking a step back. Firstly, you have to identify what software is being delivered as. It might be a container, or it might be the entire content of a machine. It might be a number of other things in between, and it's probably going to be a form factor we haven't really appreciated is coming along down the pipe, because these things change every 5 or 10 years. What I need to know is, and here I'm speaking the opposite side, if I were consuming this software, what I need to know is what you are signing up to. So what is the outside of your package, and how can you guarantee to me what tests are you running to prove that's working? If you change the operating system within your package or the libraries within your package, I don't much care as long as you keep to the same package. Now, similarly, and more problematically, if we're talking something like Kubernetes or OpenStack for that matter, or VMware, any of these things, what does the infrastructure promise, and how does it maintain that promise over life cycle versions? To my mind, this is not a question of how you do it. Do I make sure that an operating system version is maintained for 10 years? Well, you could do that. That's one possibility. It's a question of what your promise is. If you can tell me what your promise is, I can work with that. And often promises that are overly broad, as in, this is how the software looks from the outside and I promise that it works, are actually more useful to me than this runs on only Red Hat version 7 and no other, and will never run on another. And so your Red Hat version 7 has got to be working forever.
Okay, if you could build one tool to make IPUs or DPUs easier to use for edge computing, what would that be?
I would certainly say a simulator, potentially a multi-node simulator, because I'm working with networks. Networks never are a single device. They're often multiple devices. I think that would be the thing that told me whether or not I was making something that worked.
Great. So that's the end of the questions. Ian, thank you very much.